Imagine this for a moment, just over 4 light-years away, circling the closest star to our own. There exists a world that could, at least in theory, support life. A planet known as Proxima b. In the language of astronomy, that distance feels almost intimate, almost within reach. And yet, between us and that distant world lies a vast emptiness so immense that even our most advanced spacecraft would barely make a meaningful dent in the journey. Decades of technological progress, bold new propulsion ideas, and carefully designed missions have brought us far, but not nearly far enough. This closest destination beyond our solar system remains, in any practical sense, out of reach. In this quiet exploration, we will take our time to understand why traveling to Proxima b stands among the most difficult challenges humanity has ever considered. What would it truly take to cross the space between stars? And why does the universe seem to place such immense distances between the places we long to explore? If you find yourself drawn to these kinds of slow, thoughtful journeys through the cosmos, consider following the channel and staying with us for more. For now, let us gently begin our journey into the vast distance that separates us from our nearest stellar neighbor, 4.2 light-years. When we say it out loud, the distance to Proxima Centauri almost sounds manageable, like a small step in the immense scale of our galaxy. After all, interstellar distances are usually expressed in units far greater than this. The Milky Way itself spans 100,000 light-years, and Andromeda, our nearest galactic neighbor, rests about 2.5 million light-years away. Against such overwhelming scales, 4.2 light-years begins to feel close, almost familiar, as if it were just down the street rather than across a vast ocean. And this sense of closeness creates a subtle but powerful illusion. We hear the phrase nearest star and instinctively imagine something attainable, something that might yield to enough effort, enough creativity, enough persistence. But the number quietly misleads us. It carries a sense of simplicity that reality does not support. 4.2 feels small, comfortably within the range of distances we deal with in daily life. We travel farther than that without much thought. We take flights that last longer than that distance might suggest. The number invites comparison with human experience, even though that comparison breaks down completely. Because a light-year is not a familiar unit of distance. It is the distance light travels in a full year, moving at a speed so extreme that nothing with mass can ever reach it. When translated, 4.2 light-years becomes roughly 25 trillion miles. And to place that in perspective, the distance from Earth to Neptune, the most distant planet in our solar system, is only about 2.8 billion miles. Proxima Centauri is nearly 9,000 times farther away than Neptune. Or think of it another way. If the distance from Earth to Proxima Centauri were scaled down to the width of the continental United States, then everything in our solar system, from the Sun out to Neptune, would fit within the length of a single city block. Every place humanity has ever visited, every world we have seen up close, every spacecraft we have sent into the darkness, all of it exists within that single block. Meanwhile, Proxima Centauri would sit on the opposite coast, separated by thousands of miles of empty space in this scaled comparison. And this sense of nearness becomes even more misleading when we consider what lies around us. Within a sphere extending 4.2 light-years in every direction, there are only 3 stellar systems: Proxima Centauri itself, along with its companions Alpha Centauri A and Alpha Centauri B. Beyond this small region, the next closest stars are significantly farther away. Barnard's star at about 6 light-years, and Wolf 359 at nearly 8. We live in a relatively quiet and sparse corner of the galaxy, which means our nearest neighbor is not just the closest destination. but effectively the only one that even begins to resemble a reachable target for interstellar exploration. And so this apparent closeness creates a quiet paradox. For decades, it has shaped both scientific thinking and public imagination, suggesting that the first journey beyond our solar system might be just within reach. Yet in reality, even this nearest destination remains far beyond what our current technology, and even our near-future technology, can truly achieve. In 2016, astronomers revealed a discovery that changed how we think about this nearby star system. Observations from the European Southern Observatory, using the HARP spectrograph in Chile, confirmed the presence of a planet orbiting within the habitable zone of Proxima Centauri, a world now known as Proxima b. Scientists detected a subtle wobble in the motion of Proxima Centauri, a small but measurable shift caused by the gravitational pull of an unseen planet orbiting the star. That quiet signal revealed something remarkable. Proxima Centauri was no longer just our nearest stellar neighbor, but part of a system that might host a world where life could exist. The planet itself challenged many of our assumptions about habitability. Proxima b completes one orbit in just over 11 days, traveling at a distance of roughly 4.6 million miles from its star, far closer than Mercury is to the Sun. And yet, this closeness does not necessarily mean extreme heat, because Proxima Centauri is a red dwarf, smaller and cooler than our Sun. At that distance, Proxima b receives about 65% of the energy that Earth receives from the Sun, placing it within what we call the habitable zone, where liquid water could, in principle, exist on the surface. Estimates of its mass add another layer of interest. The planet appears to be at least 1.3 times the mass of Earth, suggesting a solid, rocky world rather than a gas giant. This places it firmly among potentially terrestrial planets, worlds with surfaces where familiar chemical processes might unfold. And taken together, these details seem almost too well aligned. Our nearest star, hosting a roughly Earth-sized planet, positioned within a region where life could be possible. It is as if the universe has placed a potentially habitable world at the closest possible distance beyond our solar system. This discovery changed the way we think about interstellar travel. Before Proxima b, the idea of traveling to other stars remained distant and abstract, focused on systems far beyond our ability to study in detail. The Kepler mission revealed thousands of exoplanets, but most of them orbit stars hundreds or even thousands of light-years away. Proxima b offered something different, a specific destination, a nearby target that combined scientific importance with relative proximity. It turned interstellar travel from a distant idea into something that felt, at least conceptually, like a goal. The timing was also significant, arriving as our ability to study distant planets was rapidly improving. Within just a few years, astronomers began investigating the possibility of an atmosphere around Proxima b, searching for signs of habitability or even biological activity. Each new observation refined our understanding, but also raised new questions. Can the planet hold on to its atmosphere, despite frequent stellar flares? Is it tidally locked, with one side in constant daylight? Could liquid water exist on its surface, or perhaps beneath layers of ice? These uncertainties gradually elevated Proxima b from a simple data point to something far more meaningful. For the first time, we knew of a specific world, orbiting a visible star, where the conditions for life might exist. It was no longer just a distant signal in our instruments. It became a place, a destination, a world that might one day help answer whether life exists beyond Earth. And to understand why reaching that world is so extraordinarily difficult, we first need to slow down and truly consider what 4.2 light-years actually means. Light, the fastest thing in the universe, travels at about 186,000 miles every second. Over the course of a full year, without stopping or slowing. It covers nearly 6 trillion miles. Multiply that distance by 4.2, and you arrive at roughly 25 trillion miles. The immense gap between us and Proxima Centauri. Numbers like these are difficult to grasp. Human perception evolved to understand distances we could walk, or at most travel across oceans. Distances measured in trillions simply do not fit naturally within our intuition. So we turn to analogies, to scaled-down models, trying to translate this vastness into something our minds can quietly hold. Imagine the Earth reduced to the size of a grain of sand. At that scale, the Moon would sit just a few millimeters away, close enough to pick up between your fingers. The Sun would appear as a small marble, resting about 6 feet away. Neptune, at the far edge of our solar system, would lie roughly 200 feet away, across a large room or perhaps down a long hallway. And Proxima Centauri, at this same scale, would be placed about 300 miles away, a distance similar to traveling from London to Edinburgh, or from Los Angeles to San Francisco. Everything we have ever explored, every probe we have launched, every spacecraft that has carried our instruments to distant worlds, has remained within that room, within that hallway. Not one has traveled even a small fraction of the distance to that distant city which represents our nearest star. And if we shift our perspective from distance to speed, the picture becomes even more still. A commercial airplane travels at about 560 miles per hour. At that speed, reaching Proxima Centauri would take around 5 billion years, longer than Earth itself has existed, longer than complex life has evolved here. Even if we consider the speed of the International Space Station, moving at roughly 17,000 miles per hour, the journey would still take more than 160 million years. Our fastest spacecraft, the Parker Solar Probe, reaches speeds close to 125,000 miles per hour during its closest passes to the Sun. Remarkable by any human measure. And yet, at that speed, the journey to Proxima Centauri would still take over 25,000 years. These comparisons reveal something difficult to accept. The distances between stars exist on a scale so far removed from human experience that even our fastest machines begin to feel almost motionless. We measure progress in kilometers per second, celebrating each improvement in efficiency, each new record. But the distances we are trying to cross demand something entirely different. They require speeds that are meaningful fractions of the speed of light, not just faster engines, but a completely different scale of motion. This mismatch lies at the heart of the challenge. The universe is structured with immense stretches of emptiness between the islands of matter we call stars. And for a species that evolved on the surface of a single planet, hoping to reach others, those distances present a barrier that goes beyond engineering alone. Voyager 1, launched in 1977, remains the most distant object humanity has ever sent into space. It travels at about 11 miles per second, a speed that feels extraordinary by any standard we experience on Earth. That is more than 38,000 miles per hour, fast enough to circle the planet in well under an hour. Yet even after nearly half a century of continuous travel, after covering more distance than any human-made object in history, Voyager 1 has only just begun to enter interstellar space. In 2012, it became the first spacecraft to leave the heliosphere, the vast bubble shaped by the Sun's influence. But even that milestone, as remarkable as it is, represents only the very beginning of a much larger journey. This achievement, celebrated across the world, marked a true milestone in exploration. And yet, it needs to be held alongside a quieter perspective. Voyager 1 now sits about 15 billion miles from Earth, a distance that sounds immense until we recognize that it equals only a tiny fraction of a single light year. After nearly 5 decades of travel, it has covered just 0.002 of one light year. At its current speed, Voyager 1 would need around 76,000 years to travel the 4.2 light-years to Proxima Centauri, and even that assumes it were heading in the right direction, which it is not. The spacecraft is moving toward the constellation Ophiuchus, far from our nearest stellar neighbor. Even if it could somehow be redirected, the gap in time would be almost impossible to comprehend. By the time it arrived, humanity would be separated from that moment by thousands of generations. Civilizations would come and go, languages would shift beyond recognition. The world that launched Voyager would feel as distant to those future observers as the earliest farming societies feel to us today. On board, the probe carries its well-known golden record, a small collection of sounds and images meant to represent life on Earth. Greetings in different languages, music from across cultures, fragments of what it means to be human. It is a quiet and thoughtful gesture, like a message set adrift into an endless ocean. But the reality is more still than that image suggests. Voyager 1 will spend millions of years drifting through the galaxy before it even comes close to another star system. Most of its journey will unfold in complete darkness, crossing the empty spaces between stars. None of this diminishes what Voyager represents. It stands as a remarkable achievement, a testament to human curiosity and persistence. The knowledge it has returned about the outer edges of our solar system and the boundary of interstellar space has been invaluable. But as an example of interstellar travel, it reveals something more sobering. After half a century, our most distant spacecraft has traveled a distance that is almost negligible on the scale between stars. A quiet reminder of the gap between what we have done and what would be required to reach Proxima b. To arrive there within a single human lifetime, our spacecraft would need to reach speeds far beyond anything we have ever achieved. And that raises a simple question. What do we mean by a human lifetime in this context? If we imagine a span of about 100 years, longer than most lives but still within the realm of possibility, then covering 4.2 light-years within that time would require a constant speed of about 4% of the speed of light, or roughly 7,500 miles per second. That is more than 700 times faster than Voyager 1. And even then, a century is still a long time. The people who design and launch such a mission would almost certainly never see its conclusion. And history has shown that sustaining support for projects that stretch across decades without immediate results is never easy. So we can push the idea further and imagine a journey lasting around 50 years, still longer than most careers, but perhaps short enough that some of those involved in its launch might one day witness its arrival. To make that possible, a spacecraft would need to travel at roughly 8% of the speed of light, or about 15,500 miles per second. That represents a dramatic increase, requiring speeds more than 1,400 times greater than Voyager 1. Some of the most optimistic projections go even further. A journey completed in 20 years would demand velocities approaching 20% of the speed of light, close to 37,000 miles per second. At that scale, the rules begin to shift slightly. Relativistic effects start to appear. Time itself behaves differently, with the spacecraft experiencing a little less passage of time compared to observers on Earth. Reaching such velocities, however, is not simply a matter of building larger rockets or refining existing engines. The challenge becomes far more fundamental. Energy requirements rise steeply because kinetic energy increases with the square of velocity. Doubling the speed requires 4 times the energy. Tripling it demands 9 times. And the pattern continues upward. At around 20% of light speed, even a very small probe would carry an amount of kinetic energy comparable to thousands of nuclear explosions. That energy must come from somewhere, whether stored on board as fuel, collected along the journey, or delivered from distant sources. Each possibility introduces its own set of difficult limitations. And the pursuit of such speed brings additional complications that build on top of the original problem. At these extreme velocities, the interstellar medium becomes far less forgiving. Tiny particles of dust and sparse gas, usually harmless, turn into a stream of high-energy impacts. A single grain of sand, encountered at such speed, would strike with the force of an explosive blast. Protecting the spacecraft becomes essential, yet any added shielding increases mass, which in turn demands more energy, leading back to the same cycle of escalating requirements. Navigation also becomes far more delicate. At these speeds, a spacecraft would travel the distance between Earth and the Moon in just a few seconds. Even the smallest deviation in direction could grow into a massive error over the course of the journey. Adjustments would need to be planned long in advance, because communication delays stretch into years, making real-time control impossible. Instead, the spacecraft would need to function almost entirely on its own, following instructions prepared long before launch, with no ability to respond to unexpected conditions along the way. And underlying all of this is a piece of mathematics that quietly governs every attempt at space travel. This relationship, known as Tsiolkovsky's rocket equation, was formulated more than a century ago. It links together a rocket's change in velocity, the speed at which it expels propellant, and the ratio between its starting mass and its final mass. The equation appears simple, almost elegant, yet its consequences for interstellar travel are deeply restrictive. As the target velocity increases, the amount of fuel required does not rise in a steady line, but grows exponentially, quickly reaching levels that become difficult to even imagine. In practical terms, even small increases in speed require disproportionately large amounts of fuel. And since fuel itself has mass, more fuel is needed to accelerate that fuel, which then adds even more mass, creating a feedback loop that rapidly becomes unmanageable. For missions within our own solar system, this challenge remains manageable. We can send spacecraft to places like Mars or Jupiter by accepting a simple compromise. Most of the launch mass is fuel. While the actual payload is only a small portion of the total, the mathematics still holds together, just barely, because the required changes in velocity are relatively modest. But when we shift our focus to interstellar travel, that balance begins to fall apart entirely. To reach even 1% of the speed of light using conventional chemical rockets, the fuel requirements become almost impossible to justify. For every single kilogram of spacecraft, you would need on the order of 1,000 trillion kilograms of fuel, and that is not an exaggeration. Not an 1,000 trillion kilograms for just 1 kilogram of payload. In more familiar terms, this would mean carrying fuel masses comparable to entire mountains, or even planets, and in extreme cases approaching the mass of multiple Earths, just to move the smallest probe. And this limitation is not unique to chemical propulsion. Even when we turn to more advanced systems that expel mass at much higher speeds, the underlying relationship remains unchanged. We can improve the efficiency, reduce the scale slightly, but the exponential growth cannot be avoided. Nuclear propulsion offers some relief. Reactions such as fission or fusion release far more energy per unit mass than chemical fuels, ion engines, which accelerate particles to extremely high speeds, also increase efficiency in meaningful ways. Yet even these more advanced approaches cannot escape the core limitation. When we aim for velocities that represent a noticeable fraction of the speed of light, this mathematical barrier has pushed scientists toward more unconventional ideas. If carrying fuel becomes impractical, perhaps it could be collected along the journey itself. Concepts like the Bussard ramjet suggest gathering hydrogen from interstellar space as fuel. And if carrying reaction mass proves too difficult, perhaps propulsion could rely on entirely different principles, such as laser-driven sails or solar sails that use the pressure of light itself. Each of these ideas attempts not to defeat the rocket equation, but to work around its constraints. And in doing so, the equation teaches something deeper. The universe is governed by mathematical limits that cannot simply be engineered away. We can search for alternatives, refine our methods, and explore creative solutions. But we cannot expect that building larger rockets or stronger engines alone will allow us to cross the distances between stars. Traditional rocket engines, the same kind that carried humans to the moon and sent probes throughout the solar system, rely on chemical reactions to produce thrust. Fuel and oxidizer combine, releasing energy that heats gases, which then expand rapidly and exit through a nozzle, pushing the spacecraft forward. This method has powered every journey beyond Earth's atmosphere. From the Saturn V rockets of the Apollo era to the systems that helped assemble the International Space Station. Within the solar system, chemical propulsion remains reliable and well understood, but its limitation becomes clear when we look at the speed of the exhaust it can produce. The fastest chemical rockets we have ever built expel their propellant at only a few miles per second. Impressive when compared to everyday speeds, even to the speed of sound, yet completely insufficient for interstellar travel. Because to reach another star, a spacecraft would need to move not at a few miles per second, but at thousands, or even tens of thousands of miles per second. When your exhaust velocity is measured in single digits, trying to achieve speeds thousands of times greater leads to fuel requirements that become almost impossible to grasp. And the numbers quickly move beyond anything familiar. To accelerate even a very small probe to just 1% of the speed of light, using chemical propulsion, would require a fuel-to-payload ratio on the order of 1 quintillion to 1. In simpler terms, for every single kilogram of spacecraft, you would need a billion kilograms of fuel. To place that in context, the mass of Earth itself is about 6 billion trillion kilograms. The amount of fuel required would exceed the mass of our entire planet many times over, just to send a single kilogram probe on a journey that would still take centuries to reach Proxima Centauri. Even if we could somehow store such an amount of fuel, the practical reality of gathering it would remain unsolved. Where would that material come from? Even if the entire Earth were converted into propellant, it would still fall short. There is simply not enough accessible material within our solar system to support such a mission. The requirements extend beyond the resources of a single planet, or even several combined. And these figures are not speculative. They arise directly from the well-understood physics of chemical reactions and rocket propulsion. Chemical bonds can release only a limited amount of energy for a given mass. This sets a strict upper boundary on exhaust velocity, which in turn limits the speeds a spacecraft can achieve through the unyielding mathematics of the rocket equation. No refinement in fuel chemistry, no improvement in engine design, no clever engineering workaround can bypass these thermodynamic limits. This is why chemical propulsion, despite all its success, effectively reaches its limit within our solar system. The same technology that carried humans to the moon and enabled exploration of Mars and the outer planets cannot simply be extended to reach the stars. The difference between what chemical rockets can achieve and what interstellar travel requires is not a matter of gradual progress. It is a divide that calls for entirely new approaches. And perhaps one of the most difficult ideas to accept is this: that humans themselves may not be able to make such journeys. This realization runs counter to the stories we often tell about exploration. We imagine astronauts standing on distant worlds, watching unfamiliar skies, leaving footprints on alien ground. These images shape our expectations and inspire our ambitions. Yet the reality suggested by physics is quieter and far more limiting. And yet, when we look more closely, the physics of interstellar travel makes human missions far more difficult than robotic ones, perhaps to the point of impossibility. Human life depends on a complex system of support. We require air to breathe, water to drink, food to sustain us, stable temperatures, protection from radiation, and systems to recycle waste over long periods. A spacecraft designed for humans would need to carry or continuously produce all of these resources for the entire duration of the journey. for a mission lasting around 50 years, even with near-perfect recycling. The total mass becomes enormous. Water alone, needed for drinking, hygiene, and cooling, amounts to several pounds per person each day. Food, even in highly efficient forms, adds even more. And beyond basic survival, there is the question of living space. The habitat would need to be large enough to support mental well-being over decades of isolation. Then there is radiation. In interstellar space, far from the protection of a star's magnetic field, high-energy particles pass through continuously. These can damage cells, increase long-term health risks, and gradually degrade onboard systems. To reduce this exposure, effective shielding is required, often involving thick layers of water or hydrogen-rich materials surrounding the crew. This alone could weigh hundreds of tons, all of which must be accelerated to extreme speeds and eventually slowed again. When we compare this to a robotic probe, the contrast becomes clear. Machines do not need air, water, or food. They can endure temperature extremes and radiation levels that would be fatal to humans. They do not experience isolation or psychological strain. A robotic spacecraft can be extremely small, in some cases weighing only a few grams, while still carrying essential instruments such as cameras and sensors. The difference in mass between a human spacecraft and a tiny probe could span many orders of magnitude. And because mass directly determines the energy required for acceleration, this difference becomes decisive. Time introduces another layer of difficulty. Even traveling at a significant fraction of the speed of light, a journey could take decades, long enough for aging, health complications, and psychological strain to become serious concerns. Slower missions might last longer than a single lifetime, requiring technologies like suspended animation, which we do not yet possess, or generation ships, where entirely new generations are born and live out their lives during the journey. Both possibilities introduce challenges that extend far beyond engineering. But recognizing these limits is not a form of pessimism. It is a form of clarity. Robotic exploration is not a lesser achievement. It reflects an understanding that machines can extend our reach far beyond what our bodies can endure. The rovers on Mars are still part of human exploration, even though no person stands beside them. And in the same way, a probe reaching Proxima B would represent a profound human accomplishment. The knowledge it gathers, the questions it helps answer, and the perspective it offers would still belong to us, regardless of whether the journey is made by flesh or by silicon. Ion engines represent a meaningful step forward beyond traditional chemical rockets, using electric fields to accelerate charged particles and generate thrust with far greater efficiency. Instead of burning fuel, these systems ionize a propellant, often xenon gas, removing electrons to create charged ions. These ions are then pushed through electric fields and expelled at very high speeds. The exhaust produced can reach velocities around 10 times greater than those of chemical rockets, sometimes exceeding 25 miles per second. This increase directly improves fuel efficiency through the rocket equation. And importantly, this is not just theory. Missions like NASA's Dawn spacecraft have successfully used ion propulsion to travel to Vesta and Ceres, becoming the first to orbit two separate worlds beyond Earth. Other missions have followed similar paths. The European Space Agency's Smart 1 reached the Moon using ion drives, and Japan's Hayabusa missions relied on them to collect samples from asteroids. These examples show that ion propulsion is not speculative, but a proven and reliable technology in space. However, this efficiency comes with a trade-off. The thrust produced is extremely small, often comparable to the gentle pressure of a few coins resting in your hand. Even at full power, the force generated is minimal. This means acceleration happens very slowly, building up over weeks or months of continuous operation. Within our solar system, this is acceptable. Spacecraft can take their time, gradually increasing speed without the need to escape strong gravitational pulls for long durations. But when we consider interstellar travel, the limitations become clear. Even with much higher exhaust velocities than chemical rockets, ion engines still fall far short of what is required. Reaching even a small fraction of the speed of light would demand fuel masses thousands of times greater than the spacecraft itself. The journey time would stretch far beyond practical limits. Estimates suggest that a spacecraft using ion propulsion would need more than 40,000 years to reach Proxima Centauri. While this is an improvement over chemical propulsion, it remains far beyond any meaningful mission timescale. There is also the question of power. Ion engines depend on a steady supply of electricity to function. Near the Sun, this can come from solar panels, while missions deeper into the solar system rely on radioisotope generators. But once a spacecraft moves far beyond the Sun's influence, solar power becomes ineffective, and current power sources cannot provide enough energy to sustain the required thrust. In theory, a nuclear reactor could provide the necessary power for ion engines, but adding such a system also increases the spacecraft's mass, reducing much of the advantage gained from higher efficiency. Even so, ion propulsion represents real progress, expanding what we can achieve within our solar system and enabling missions that would be difficult or even impossible with chemical rockets alone. Yet when we look beyond the solar system, ion engines begin to reveal a familiar limitation. Even large improvements over conventional designs still fall short when faced with interstellar distances. This leads us to another step forward: nuclear thermal rockets, which use reactors to heat propellant to extremely high temperatures before expelling it to produce thrust. The idea itself is relatively simple. A nuclear reactor generates intense heat through fission, and that heat is transferred to a propellant, usually liquid hydrogen. The propellant expands rapidly and exits through a nozzle, creating thrust. Because nuclear reactions can reach much higher temperatures than chemical combustion, the exhaust velocity can be roughly twice that of traditional rockets. This increase improves efficiency and reduces the amount of propellant needed for a given mission. During the 1960s and early 1970s, NASA conducted extensive tests of this technology under programs such as NERVA. These experiments showed that nuclear thermal engines could operate reliably, maintaining stability even under extreme conditions while delivering the expected performance gains. The program was eventually discontinued, not because it failed technically, but due to changing priorities and limited funding as the Apollo era came to an end. In recent years, interest in nuclear thermal propulsion has returned, especially for missions to Mars, where faster travel could reduce both radiation exposure and the psychological strain on astronauts. Within the solar system, the advantages are clear. A nuclear thermal rocket could shorten a journey to Mars from many months to a significantly shorter duration, while also allowing more payload and less fuel. For missions to the outer planets, the same efficiency would enable more ambitious exploration. But when we extend this approach to interstellar travel, the same limitation appears once again. Even with improved exhaust velocities, nuclear thermal rockets still operate at only a few miles per second, far below the thousands of miles per second required to reach another star within any reasonable time. When the rocket equation is applied at these scales, the result becomes familiar. Fuel requirements rise to levels millions of times greater than the payload, reinforcing the same fundamental barrier that has shaped every propulsion method we have considered so far. Even with these improvements, the journey time would still extend beyond 40,000 years to reach Proxima Centauri. An improvement over chemical propulsion, certainly, but still far longer than all of recorded human history. And the presence of a reactor introduces further complications. Nuclear systems require shielding to protect both onboard equipment and any potential crew from radiation. They also demand cooling systems to prevent overheating, and fuel elements capable of enduring extreme temperatures without failure. All of this adds significant mass, which must be accelerated along with the spacecraft itself. Within our solar system, this added weight is acceptable because the gains in efficiency outweigh the cost. But for interstellar missions, where the required velocities are so extreme, the reactor's mass becomes a serious limitation. It reduces much of the benefit it was meant to provide. Nuclear thermal propulsion represents real progress and could greatly improve how we explore nearby worlds. Yet, like ion engines and other advanced concepts, it shows that even meaningful improvements still leave us far from what interstellar travel requires. The gap between our most advanced designs and what would be needed to reach Proxima b within a human timescale remains vast. Another approach takes a different path entirely. The Variable Specific Impulse Magnetoplasma rocket, often referred to as VASIMAR, is one of the most advanced plasma propulsion systems developed so far. It uses radio waves to heat a gas, such as argon or hydrogen, into plasma at temperatures exceeding 18,000 degrees Fahrenheit. Powerful magnetic fields then contain and guide this plasma, directing it out of the engine to produce thrust. What makes this system unique is its flexibility. It can be adjusted to provide higher thrust with lower efficiency or lower thrust with much greater efficiency, depending on the needs of the mission. The technology has been tested extensively on the ground. Experiments have shown stable plasma generation, effective magnetic control, and thrust levels that align closely with theoretical predictions. The engine can operate for long periods without significant wear, suggesting it could be suitable for extended missions. There has been growing interest in using this system for missions to Mars, where its efficiency could shorten travel times compared to conventional propulsion. At first glance, the performance appears promising. With enough onboard power, a spacecraft using this engine could accelerate continuously, slowly but steadily building up speed over time. Supporters of this technology suggest it could shorten a journey to Mars from around 18 months to just over a month, a dramatic shift that would reduce radiation exposure and ease the psychological strain of long missions. For travel deeper into the solar system, similar benefits appear, with faster transit times and lower propellant demands. And yet, even this highly advanced system falls far short when we look toward the stars. Despite its advantages over both chemical and nuclear thermal propulsion, a spacecraft using this method would still take roughly 2,200 years to reach Proxima Centauri. The core limitation remains the same. While exhaust speeds are higher, they are still far below what is needed for true interstellar travel. There is also the matter of power. To produce meaningful thrust, the engine would require enormous amounts of electrical energy, tens or even hundreds of megawatts, likely supplied by onboard nuclear reactors. But adding such power systems increases the spacecraft's mass, introducing the same trade-offs seen in earlier designs. Efficiency, while improved, is not perfect. A significant portion of the energy is lost as heat, which must be released into space through large radiator systems. These structures alone could weigh many tons. And all of it, the reactor, the radiators, the propulsion system itself, must be accelerated alongside the payload. So while this technology represents a genuine step forward and may transform how we explore our own solar system, it does little to close the gap to the stars. A journey lasting over 2,000 years, though shorter than earlier estimates, still spans a time longer than much of recorded human civilization. In this way, it quietly reinforces a recurring lesson. Even major technological advances leave us confined to our local neighborhood, unable to bridge the vast distance to even the nearest star. Some ideas, however, attempt to take a far more radical approach. One of the most striking is known as Project Orion, a concept that proposes moving a spacecraft forward by detonating nuclear explosions behind it. This idea first emerged in the late 1950s at Los Alamos, where scientists including Freeman Dyson and Ted Taylor explored the physics of nuclear pulse propulsion. The design envisioned a large spacecraft equipped with a massive metal plate at its rear, supported by shock-absorbing structures. Nuclear charges would be released behind the vehicle at regular intervals, detonating at a controlled distance. The force of each explosion would strike the plate, and the shock absorbers would smooth the impact into forward motion. At first glance, the concept seems extreme, almost difficult to take seriously. And yet, the underlying physics proved to be sound. Experiments using conventional explosives showed that the basic principle could work. Calculations suggested that such a system could achieve exhaust velocities far beyond chemical rockets, potentially reaching a few percent of the speed of light if more advanced nuclear devices were used. The idea gained significant attention in the early 1960s. Detailed studies produced designs that, while ambitious, were technically grounded. The spacecraft envisioned would be enormous, weighing hundreds of thousands of tons, with a large plate designed to endure repeated nuclear blasts. The mission profile involved launching hundreds of thousands of small nuclear devices, detonating them in sequence over extended periods of acceleration. Each explosion would add a small increase in speed, gradually building toward the velocities required for interstellar travel. With more advanced designs, the journey to Proxima Centauri could, in theory, be completed in around 150 years. This begins to approach something closer to possibility, at least in abstract terms. A generation ship using such propulsion might complete the journey, with future generations arriving at a destination their ancestors set out to reach. The idea led to serious conversations about multi-generational spacecraft and the kinds of social systems that would be required to sustain them over centuries. But in reality, many barriers prevented Project Orion from ever becoming a real mission. The Partial Nuclear Test Ban Treaty of the early 1960s prohibited nuclear detonations in space, effectively ending its legal feasibility. There were also environmental concerns. Launching a spacecraft filled with nuclear devices from Earth raised risks that were difficult to justify. The cost alone. Building such a massive structure and producing hundreds of thousands of nuclear charges would have placed enormous strain on even the largest economies. And during the Cold War, the idea of sending nuclear weapons into space, regardless of purpose, was politically unacceptable. Even if these challenges could have been overcome, the results would still fall short of making interstellar travel practical. A journey lasting around 150 years is still extraordinarily long, longer than the lifespan of modern nations, longer than entire eras of human development, and maintaining a spacecraft, along with a functioning human society, over such time introduces challenges as complex as the propulsion itself. If a single lifetime is not enough, then perhaps the only alternative is to think in terms of generations. The concept of a generation ship suggests a self-contained world, carrying hundreds or even thousands of people across the stars over many centuries. The original crew would live and die aboard the vessel, raising children who have never seen Earth. And those children would continue the journey, passing it forward until distant descendants finally arrive. In this way, the destination would not belong to those who began the mission, but to those born along the way. It is an idea that carries a certain quiet appeal. Humanity extending itself across time, families bound together by a purpose that no single life could complete. Science fiction has explored this vision in many forms, imagining the cultures that might emerge in such isolated environments, the systems needed to preserve stability, and the deeper questions about identity and purpose that would naturally arise. In some ways, it reflects familiar patterns in human history, long projects that span generations, traditions carried forward across centuries. But the reality of building such a vessel introduces challenges that may be even more difficult than the journey itself. The spacecraft would need to operate as a fully closed system, sustaining life without interruption for hundreds of years. Every drop of water, every breath of air, every nutrient would need to be recycled with near-perfect efficiency. Even small losses would accumulate over time, A failure rate of just a fraction each year could lead to total collapse within a century. And no system humanity has ever built has demonstrated that level of long-term reliability. Beyond survival, the environment would need to support a stable and healthy society. That means agriculture to produce food, manufacturing to repair and replace equipment, medical systems capable of handling both routine care and emergencies, and education to pass knowledge forward across generations. It would also require space for recreation and mental well-being, to prevent the slow decline that can come from permanent confinement. In many ways, the challenge begins to resemble sustaining a small town, except this town would exist in deep space, completely isolated, with no possibility of outside help. And even then, biological factors introduce further complexity. A limited population risks reduced genetic diversity over time, which can lead to long-term health problems. To avoid this, the initial population would need to be large enough to maintain genetic variation, likely numbering in the hundreds. But supporting such a population over centuries significantly increases the demands on life support and habitat size. Some proposals suggest storing genetic material to introduce diversity later. But this raises difficult ethical questions about future generations shaped by decisions made long before their existence. The social challenges may, in the end, prove even more difficult than the technical ones. How do you preserve a shared sense of purpose when no one alive remembers Earth, or the reason the journey began? What prevents divisions from forming, beliefs from splitting, or conflicts from emerging within a society that has no external reference point? And how do you ensure that critical knowledge is passed down, when each generation may feel disconnected from a destination they will never see? These questions reach into the deeper layers of human behavior and social structure, in ways that engineering alone cannot fully resolve. Shifting away from these long journeys, another idea takes inspiration from something far more subtle. Solar sails do not rely on wind in the traditional sense, but on radiation pressure, the gentle push carried by light itself. Photons may have no mass, yet they do carry momentum. When they strike a reflective surface, they transfer that momentum, much like a ball bouncing off a wall imparts a small push. The force involved is extremely small. At Earth's distance from the sun, sunlight exerts only a tiny pressure, comparable to the weight of a single grain of sand spread across a wide surface. But in the frictionless environment of space, even this faint push can slowly accelerate a spacecraft over time. The idea itself is not new. Centuries ago, Johannes Kepler suggested that sunlight might influence the motion of comet tails, but only in recent decades has the technology become practical. To work effectively, a solar sail must be incredibly thin and lightweight, maximizing surface area while remaining strong enough to deploy and hold its shape. Modern designs use materials just a few microns thick, thinner than a human hair, often made from reflective films or ultra-thin metals. These delicate structures can be folded tightly for launch, then carefully unfurled in space to form sails spanning large areas. A notable example is Japan's Ikaros spacecraft, which demonstrated solar sailing by traveling from Earth toward Venus using light pressure alone. The mission showed that the concept worked outside of theory. The sail deployed successfully, remained stable, and produced measurable changes in trajectory. It marked an important step forward, the first time a spacecraft moved between planets using only the pressure of sunlight once it had left Earth's immediate influence. However, when we consider journeys beyond the solar system, limitations begin to appear. The strength of sunlight decreases rapidly with distance. By the time a spacecraft reaches the orbit of Jupiter, the available pressure has dropped to only a small fraction of what it is near Earth. Farther out, the effect becomes almost negligible. Beyond the outer boundary of the sun's influence, sunlight provides virtually no propulsion at all. Any meaningful acceleration must happen close to the sun, where radiation is strongest. This requirement forces spacecraft to pass deep into the inner solar system, where temperatures rise to extreme levels. At such distances, the sail material must endure intense heat without losing its shape or reflective properties. Even the most carefully chosen materials struggle under these conditions. The spacecraft itself must also be protected, using shielding to prevent its systems from being damaged by the surrounding heat. Even under near-ideal conditions, with a sail of enormous size, a spacecraft of extremely low mass, and a trajectory that passes as close to the Sun as materials can endure, the journey to Proxima Centauri would still take somewhere between 1,000 and 2,000 years. Solar sails alone cannot resolve the challenge of interstellar travel. And yet, missions like Icaros have shown that the concept itself is very real. These delicate, almost weightless structures are capable of moving spacecraft through space. Launched in May 2010 alongside the Akatsuki mission to Venus, Icaros carried a square sail measuring about 46 feet across. Made from an ultra-thin film only a few microns thick, the material, far thinner than a human hair, was coated to reflect sunlight and embedded with small solar cells to generate power. The entire system, including the spacecraft, weighed only a few hundred kilograms. Deploying the sail was itself a major achievement. It began folded tightly during launch, then slowly opened in space as the spacecraft spun, using centrifugal force to stretch the membrane outward without the need for heavy mechanical supports. Images captured during the mission showed the sail fully extended, shimmering faintly as it caught sunlight millions of miles from Earth. More importantly, the spacecraft recorded clear evidence of acceleration caused by radiation pressure. Its instruments measured small but consistent changes in velocity, matching what would be expected from the momentum of light. For the first time, it was confirmed, not just in theory, but in practice, that sunlight alone could propel a spacecraft. Icaros continued its journey toward Venus, relying largely on this form of propulsion after its initial trajectory was set. The mission also demonstrated a subtle form of control. By adjusting how different sections of the sail reflected light, engineers were able to change the spacecraft's orientation without using fuel. This showed that solar sails could do more than move forward. They could also steer and maintain stability over long durations. In this way, Icaros validated decades of theoretical work. It helped shift solar sailing from an idea into a working technology. Later missions continued this progress. Small sails deployed in Earth orbit demonstrated controlled motion using only sunlight, gradually raising their orbits without conventional propulsion. Together, these efforts moved solar sailing into the realm of proven capability. But proving that something works on a small scale is very different from solving the much larger problem of interstellar travel. Icaros operated relatively close to the Sun, where radiation pressure is still strong, and it covered distances measured in millions of miles, not trillions. The changes in velocity it achieved, while meaningful, remain far below what would be needed for a journey between stars. In many ways, the mission highlights both success and limitation at the same time. Solar sails can work, but there is still a vast distance between demonstrating the concept and using it to cross light years of space. For a solar sail to reach truly high speeds, it must travel extremely close to the Sun, where radiation is at its most intense. The relationship is simple but unforgiving. As distance to the Sun decreases, radiation increases rapidly. Move to half the distance, and the intensity becomes 4 times stronger. To take advantage of this, mission designs often propose trajectories that pass just a few million miles above the solar surface, far closer than any planet. At such distances, the environment becomes extreme. Radiation levels can rise thousands of times beyond what we experience near Earth, creating temperatures that push the limits of material science. A solar sail passing this close would face temperatures exceeding 3,600 degrees Fahrenheit. This is close to the melting point of many metals, and far beyond what most conventional materials can tolerate. The sail must not only survive this heat, but remain stable and reflective. Even small deformations or loss of reflectivity would reduce its ability to generate thrust. Because of this, material choice becomes critical. Standard polymer films, even those designed for space, begin to break down under such conditions. Reflective coatings can degrade or even vaporize. To address this, engineers have explored more advanced materials, including carbon-based composites, ceramic films, and specialized metal alloys designed to withstand extreme heat. Some designs attempt to use the spacecraft's rotation to keep the sail stretched outward, maintaining its shape despite thermal stress. But the spacecraft attached to the sail faces its own challenges. Even if most sunlight is reflected, some energy is absorbed as heat. The spacecraft must be protected from this constant thermal load while remaining as light as possible. All onboard systems, from electronics to communication equipment, operate within temperature limits far below what this environment provides. To survive, the spacecraft requires insulation, heat shields, and radiators to release excess heat. Each of these adds weight, reducing the overall efficiency of the system. There is also the issue of time. A spacecraft cannot remain close to the sun for long. It passes through this region quickly, sometimes in a matter of days, before continuing outward. This means that most of the acceleration must occur within a short and critical window. During that brief moment, everything must function perfectly. The sail must deploy correctly, maintain its orientation, and endure the extreme heat. Any failure during this phase would end the mission entirely. Some proposed solutions try to work around these limits. One idea suggests sails that slowly shed outer layers as they heat up, allowing inner layers to continue functioning. Another approach involves multi-layered sails, where damaged sections can be discarded during flight. But each new idea introduces additional complexity. And in the end, the environment near the sun reveals a deeper truth. The closer we move toward solving one problem, the more new challenges emerge, each adding another layer to the already difficult task of reaching the stars. Combining the idea of solar sails with nuclear pulse propulsion leads to a concept known as Medusa. Instead of pushing a spacecraft from behind, it imagines pulling it forward using controlled nuclear explosions captured by an enormous sail-like structure. Developed in the 1990s by John Del Sol. This design reverses the logic of Project Orion in a rather elegant way. Rather than using a heavy plate at the rear to absorb repeated blasts, Medusa places a large, lightweight sail in front of the spacecraft, connected by long cables. Nuclear devices are detonated between the sail and the craft, and the expanding plasma from each explosion presses against the sail's surface. The force is then transferred through the cables, which also act as shock absorbers, smoothing out the otherwise violent impulses. This approach offers several advantages, because the sail does not need to endure direct contact with the explosion itself. It can be much lighter than Orion's massive structure. The blasts occur at a controlled distance, and the sail only interacts with the expanding energy and plasma. This reduction in mass improves overall efficiency, while the large surface area allows more of each explosion's energy to be captured. The spacecraft remains positioned behind the sail, shielded from much of the direct radiation. In operation, the process would be carefully timed. Small nuclear charges, perhaps comparable in size to everyday objects, would be released ahead of the craft and detonated in sequence. The sail, potentially hundreds of meters across, would catch each expanding wave, and with every pulse, the spacecraft would gain a little more speed. Over time, thousands of such detonations could gradually accelerate the craft to a meaningful fraction of the speed of light. Some estimates suggest velocities of a few % of light speed might be possible. allowing a journey to Proxima Centauri in roughly 140 years. This places the concept within the realm of multi-generational missions, long, but perhaps not entirely beyond imagination. In theory, such a system could even continue onward, using remaining energy to explore nearby stars beyond its initial destination. However, the challenges remain profound. The same political and environmental concerns that halted Project Orion would apply here as well. Launching large numbers of nuclear devices into space raises difficult questions about safety, regulation, and global cooperation. The engineering itself is equally demanding. A vast sail connected by long tethers must survive repeated exposure to radiation and plasma without losing its integrity. Each component must function reliably under conditions unlike anything we have tested before. And even with all of this, the journey would still take centuries. Medusa represents a bold and creative step in propulsion design, but it does not remove the deeper barrier. Interstellar distances remain vast, and even our most ambitious ideas struggle to cross them within a human timescale. A journey lasting over a century still lies far beyond current mission planning, requiring either generations of travelers or technologies that do not yet exist. And so, attention turns to another possibility. Instead of relying on the sun's gentle radiation, what if we used concentrated beams of light, focused and directed with precision, to push a spacecraft across the stars? This concept addresses one of the core limitations of solar sails. Sunlight becomes weaker very quickly as distance from the sun increases, meaning it can only provide meaningful acceleration during the early stages of a journey. Laser systems offer a different approach. Instead of relying on natural radiation, they can project concentrated energy across vast distances, allowing a spacecraft to accelerate continuously for months or even years, rather than just a brief period. The beam remains tightly focused, far beyond the point where sunlight becomes too weak to matter, extending the acceleration phase and allowing for much higher final speeds. The underlying physics is similar to solar sailing. Light carries momentum, and when that light reflects off a sail, it transfers a small push to the spacecraft. But lasers introduce important advantages. Because laser light is coherent and uniform in wavelength, it can be shaped into narrow beams that spread far less over long distances. The sail itself can also be engineered to match the specific wavelength of the laser, improving reflectivity and reducing energy loss. Perhaps most importantly, the power behind the system can be adjusted. Unlike the fixed output of the sun, a laser array can be scaled depending on the mission. In theory, such an array would be enormous, stretching across hundreds of square miles, and could be positioned in orbit, on the moon, or at stable gravitational points in space. Thousands of individual emitters would work together, combining their output into a single focused beam aimed precisely at the departing spacecraft. The energy involved would be immense, reaching levels comparable to multiple large power plants operating continuously. Even with perfect design, there are still limits. Over vast distances, laser beams gradually spread due to fundamental physical effects. A beam that begins narrow will slowly widen, and by the time it reaches a spacecraft far away, it may have expanded across enormous distances, reducing its intensity. To counter this, the system would require extremely large apertures, which in turn demand even more ambitious construction efforts. Precision also becomes critical. The beam must remain locked onto a spacecraft moving at extraordinary speed, across distances measured in trillions of miles. Even a small error in alignment would cause the beam to miss entirely. This means the spacecraft's position must be known with extraordinary accuracy, down to very small margins, even across light years of separation. Achieving this level of tracking goes far beyond what we are currently capable of. And yet, despite these challenges, laser-driven sails may represent one of the most promising paths forward. Calculations suggest that with enough power, a small spacecraft could be accelerated to around 20% of the speed of light. At that velocity, the journey to Proxima Centauri could take only a few decades. For the first time, interstellar travel begins to move from the scale of generations into something that could fit within a human lifetime, or at least within the lifetime of those who set the mission in motion. The idea does not break the laws of physics, and it does not rely on materials that cannot exist. But it does demand something else entirely: an enormous level of infrastructure, and engineering on a scale humanity has never attempted before. To move even a very small spacecraft to around 20% of the speed of light within a reasonable time would require laser power measured in tens of gigawatts. This is comparable to the combined output of dozens of large power plants operating continuously. That energy must be converted into a coherent beam, focused with extreme precision, and kept aligned with a target that is moving farther away every second. And the difficulty does not sit in one place. It appears at every stage, generating the power, shaping the beam, maintaining alignment, and building the physical structure to support it all. The laser array itself would be vast, stretching across hundreds of square miles. It could contain thousands, perhaps tens of thousands of individual emitters working together. Each of these elements would need to remain perfectly synchronized, combining their output into a single beam. Even a tiny misalignment, smaller than the width of a wavelength, would reduce efficiency and waste energy. Maintaining that level of precision across such a large structure, while it expands and contracts under changing temperatures, becomes a challenge of its own. Where to build such a system is another question entirely. Placing it in orbit makes construction and maintenance more accessible, but introduces constant thermal shifts as the structure moves in and out of sunlight. Building it on the moon offers a stable surface, yet lunar dust could interfere with sensitive optics, and the slow rotation of the moon complicates continuous tracking. More distant points in space provide stability, but make maintenance and repair far more difficult. And regardless of location, the system requires an immense supply of energy. Solar arrays could provide power in space, but they would need to cover vast areas to reach the necessary output. Nuclear reactors offer a more compact solution, but introduce their own challenges, especially in managing the heat they produce. That heat cannot simply disappear. In space, it must be radiated away, requiring large cooling structures. The lasers themselves also generate heat during operation, adding to the problem. Radiators, power systems, structural supports, and optical components together would create a structure with a mass measured in thousands, perhaps tens of thousands of tons. All of it would need to be launched or assembled using capabilities we have not yet developed. The financial cost would be equally significant. Even modest versions of such systems could require tens of billions of dollars, while more advanced designs might approach hundreds of billions. These are investments on the scale of major national infrastructure projects. And beyond engineering and cost, there is the question of time. Building such a system would take decades, maintaining support, both political and financial. Across that span may prove as difficult as the technical work itself. In this way, laser sail technology stands as both a promise and a challenge. It may offer a path toward the stars, but only if we are willing to commit to efforts that stretch not just our technology, but our capacity for long-term cooperation and planning. Project Breakthrough Starshot marks an important shift, moving the idea of interstellar travel from theory into early-stage engineering, supported by real funding and coordinated scientific effort. Announced in 2016 as part of the Breakthrough Initiatives, the project, backed by investor Yuri Milner and supported by scientists such as Stephen Hawking, set out with a clear goal: to send extremely lightweight spacecraft toward the Alpha Centauri system within a single generation. An initial investment of $100 million was committed to research and development, with the possibility of far greater funding if progress continues. This represents one of the first serious attempts to move beyond academic discussion and into the practical design of missions and hardware. The project brought together a wide range of expertise. Physicists, engineers, and astronomers from different fields contributed, drawing on knowledge from areas such as material science, laser systems, spacecraft design, and astrophysics. This was not a small or isolated effort, but a coordinated initiative that attracted attention from major institutions around the world. As a result, universities and research laboratories began focusing on specific challenges identified by the project, creating a distributed network of work across multiple countries, each group addressing a different piece of the problem, from propulsion to miniaturization. What makes this approach distinct is its simplicity in concept. Rather than designing massive spacecraft with entirely new propulsion systems, Starshot focuses on making spacecraft extremely small. The key insight is that reducing mass by many orders of magnitude changes the problem entirely. A spacecraft weighing just a few grams requires far less energy to accelerate than one weighing tons. And while the laser systems needed to propel such small probes are still difficult to build, they remain within the realm of possible engineering, rather than requiring unknown physics. The mission design reflects this thinking. Instead of launching a single large spacecraft, thousands of tiny probes would be sent. Some would fail, but a fraction would survive the journey. These probes would be pushed by powerful lasers acting on light sails, removing the need to carry fuel on board. Each probe would remain simple, carrying only essential instruments such as small cameras, basic sensors, and minimal communication systems. Reducing complexity helps reduce mass and increases the chances of success across many units. The mission would also avoid the need to slow down at its destination. Rather than entering orbit, the probes would perform a high-speed flyby, collecting data as they pass through the system. This removes the need for deceleration, which would otherwise require enormous additional energy. This approach accepts current limitations while still pushing forward. It does not depend on unknown materials or breakthroughs in physics, but instead identifies specific areas that must improve: laser power, beam control, miniaturization, and sail design. Even so, the timeline remains long. With sustained effort and sufficient resources, it may take several decades before the first probes are ready to launch. But for the first time, the path forward begins to feel defined. Not easy, but at least visible. Starshot has brought renewed energy to the field of interstellar exploration, showing that serious resources and serious intent are now being directed toward turning these ideas into reality. It has encouraged new lines of research, revived interest in supporting technologies, and suggested that what once felt like a distant dream might begin to take shape within this century. Whether the project ultimately succeeds or not, it marks an important shift in perspective. Interstellar travel moves from a vague possibility into something more concrete, a direction we can begin to outline and a challenge we can actively attempt. And at the center of this effort is a design that redefines what we think of as a spacecraft. The proposed probes, often called star chips, are extremely small. They would weigh only a few grams and measure just a few centimeters across. This stands in sharp contrast to traditional spacecraft, which often weigh hundreds or thousands of kilograms and include layers of redundant systems, shielding, power supplies, and fuel. Even the most compact modern satellites still weigh several kilograms. Starshot takes a very different approach. It reduces spacecraft size by several orders of magnitude, creating devices smaller than a typical handheld object, closer in scale to something as simple as a postage stamp. This is made possible by removing almost everything that is not absolutely essential. These probes carry no onboard propulsion system. All acceleration comes from the external laser pushing on the sail. Power generation is minimal, limited to tiny solar cells or stored energy, just enough to function briefly during the flyby. There is no heavy shielding against radiation or impacts. Instead of relying on durability, the design accepts that some probes may fail, and depends on launching many units to ensure that at least a few succeed. The instruments on board are kept as simple as possible. A small camera captures images during the brief passage through the system. Basic spectrometers analyze light from the star and any nearby planets, providing clues about atmospheres and surface conditions. Additional sensors measure magnetic fields and particle environments. All of this must fit within an extremely small mass budget, possibly no more than a single gram. Advances in microelectronics make this possible. Adapting technologies from everyday devices but refining them to operate in space. Communication becomes one of the most difficult aspects at this scale. Sending signals across several light years usually requires either strong transmitters or large antennas, and these probes have neither. Instead, the design suggests using the sail itself as part of the communication system, embedding structures that can direct signals back toward Earth. Even then, the data rate would be extremely low. Transmitting a single detailed image could take days, or even weeks. This means the probe must carefully choose what information to send, knowing that its opportunity to communicate is limited. Navigation adds another layer of complexity. The probe must maintain awareness of its position and orientation with enough precision to aim its instruments and communication system correctly during a very brief encounter. Tiny sensors, adapted from technologies used in everyday electronics, provide this awareness. An onboard computer, operating with very little power, processes data and follows a pre-planned sequence of actions. There is no possibility of real-time control from Earth. Everything must be decided in advance and executed exactly as intended. As the probe makes its silent passage through another star system, manufacturing devices at this scale pushes modern technology to its limits. Each star chip becomes something like a highly specialized microchip, integrating sensors, basic computation, and communication into an incredibly small form. Production would likely follow methods used in the semiconductor industry, where many units can be fabricated together on a single silicon wafer. This opens the possibility of true mass production. Instead of building one complex and costly spacecraft, thousands of identical probes could be created at relatively low cost. It represents a shift away from handcrafted machines worth vast sums, towards something closer to precision manufacturing at scale, at speeds approaching 20% of the speed of light. These tiny probes could cross the distance to Proxima Centauri in about 20 years. This represents a dramatic leap beyond anything humanity has achieved. For comparison, even our fastest spacecraft moves at only a small fraction of that speed. At such velocities, the scale becomes difficult to visualize. A probe moving this fast could circle Earth in less than a moment, or travel the distance to the Moon in only a few seconds. And reaching that speed requires an equally extreme process of acceleration. The concept relies on powerful laser arrays delivering energy continuously for a short period, perhaps several minutes, as the probe moves away from Earth. During that brief window, it must accelerate from rest to a significant fraction of light speed. The forces involved would be immense, far beyond what any human could survive, and challenging even for mechanical systems. Only because these probes are so small, with minimal internal structure, do they have a chance of enduring such acceleration without breaking apart. Even then, the energy required remains enormous. Accelerating just a single gram to these speeds demands an amount of energy comparable to that released by large explosive forces. The laser system must maintain extremely high power output throughout this phase, focusing its energy onto a sail only a few meters wide. While the probe moves away at ever-increasing speed, this creates additional complications. As the probe accelerates, the wavelength of the incoming light shifts, meaning the sail must remain reflective across a changing range of frequencies. Stability is equally important. The probe must remain correctly oriented so that the sail continues to capture the beam. Any rotation or misalignment could reduce efficiency or send the probe off course. Because of the increasing distance, control must be fully autonomous. Signals from Earth would take too long to guide the process in real time. Once the acceleration phase ends and the laser shuts off, the journey becomes passive. The probe continues forward at its final speed, with no ability to adjust course or slow down. It becomes, in effect, a carefully aimed object traveling through space. This makes precision at the beginning absolutely critical. Any small error in direction or stability cannot be corrected later. Everything depends on that initial phase, and yet, even with these constraints, a journey lasting around 2 decades begins to feel, at least in principle, within the scope of human planning. For the first time, the timeline begins to align, at least slightly, with human experience. The scientists and engineers involved in the launch might still be active when the first data returns. Public interest, often difficult to sustain over long periods, might endure across a few decades. And most importantly, the requirements, while extreme, remain grounded in known physics. Nothing here demands impossible materials or violations of natural laws. But the space between stars, though often described as empty, is not truly void. It contains a thin spread of particles, mostly hydrogen, with traces of other elements. On average, there may be about 1 atom in each cubic centimeter, far more rarefied than any vacuum we can create on Earth. Yet, at speeds approaching a significant fraction of light, even this sparse environment becomes dangerous. A spacecraft traveling at such velocity would encounter these particles as a continuous stream of impacts, each carrying substantial energy. What seems negligible at low speeds becomes destructive at high ones. The numbers quickly become sobering. At these velocities, even a single atom carries enough energy to cause measurable damage. Tiny grains of dust, almost microscopic in size, would strike with explosive force. Over the course of the journey, a probe would experience countless collisions, with atoms, with dust, and occasionally with larger particles drifting through interstellar space. The effects depend on the size of what is encountered. Individual atoms can penetrate surfaces, gradually damaging materials at the microscopic level. Over time, this leads to degradation of electronics, weakening of structural components, and loss of clarity in optical systems. It is a slow but persistent form of wear, similar to aging, but greatly accelerated. More substantial particles bring more immediate consequences. A small grain of dust could puncture the sail, weakening its structure. Repeated impacts could gradually tear it apart. A direct hit on the probe itself could destroy critical systems instantly, ending the mission without warning. Adding protective shielding might seem like an obvious solution, but it introduces the same problem seen throughout interstellar design. Extra mass requires more energy to accelerate, and for such small probes, even minor increases in weight become significant. Scientists have tried to estimate how likely these impacts are. The density of the interstellar medium varies, with some regions more crowded than others. Certain paths may pass through dust clouds, increasing the risk. Even in relatively clear regions, the probability of failure remains high for any single probe. This leads to a different strategy. Instead of relying on one spacecraft to survive, the mission would launch thousands. Each individual probe might have only a modest chance of making it through intact, but taken together, the probability shifts. Even if most are lost, a portion would still reach the destination and return data. In this way, the problem changes from an absolute barrier into a matter of probability. Success no longer depends on perfection, but on numbers. It is a quiet shift in thinking, one that accepts loss as part of the process. The approach mirrors patterns found in nature, where large numbers ensure that at least some survive. Not every seed grows, not every journey succeeds, but enough do to carry the outcome forward. And in that sense, even the harsh emptiness between the stars becomes something that can be navigated, not by avoiding risk entirely, but by working with it. Rather than committing vast resources to a single spacecraft designed to survive every possible hazard, this approach takes a different path. It proposes building thousands of identical probes at low cost, accepting that many will be lost, but ensuring that enough survive to complete the mission. The entire strategy depends on extreme miniaturization and large-scale production. Traditional spacecraft are expensive because each one is carefully designed and built as a unique system. Every component is tested extensively, and redundancy is added to minimize the chance of failure. This level of precision is necessary when only one vehicle is launched. But when thousands are sent, the philosophy changes. Instead of perfection, the focus shifts to quantity. These tiny probes could be produced using methods similar to those used in semiconductor manufacturing, treating spacecraft more like microchips than custom machines. A single production cycle might yield thousands of identical units, reducing the cost of each probe significantly. If each one costs only a small fraction of a traditional spacecraft, then losing most of them becomes acceptable. The solution is simple in principle. Launch more probes to account for expected losses. The numbers become predictable. If only a small portion survive, then increasing the total number launched ensures that enough will still reach the destination. This creates a system where mission planners can adjust scale based on available resources and desired outcomes. It also provides a form of protection against the unknown. If interstellar space turns out to be more hostile than expected, with higher densities of dust or radiation, the overall mission can still succeed because it does not depend on any single probe. Launching such a fleet introduces its own advantages. A larger carrier spacecraft could release these tiny probes one after another while in orbit. Each would deploy its sail and be accelerated individually by laser systems. This staggered approach spreads the workload over time. Rather than requiring all probes to launch at once, different probes might follow slightly different paths, sampling various regions of interstellar space. Even if many fail, those that survive could return a range of data, offering a broader picture of the journey. In this way, interstellar exploration begins to resemble something less precise and more statistical. Instead of relying on one perfect attempt, it becomes a process of many attempts, where success emerges from probability rather than certainty. But sending probes across the distance is only part of the challenge. They must also communicate their findings back to Earth, and this introduces another layer of difficulty. Signals traveling across several light years spread out as they move, becoming weaker with distance. By the time a transmission arrives, it is reduced to an extremely faint trace. Detecting such a signal requires highly sensitive instruments and large receiving systems capable of separating meaningful data from background noise. At the same time, the probe itself has very limited capability. With such a small mass, it cannot carry large antennas or powerful transmitters, and so, even after completing the journey, the final challenge remains: finding a way to be heard across the vast silence between the stars. The entire communication system would operate on only a tiny amount of power, comparable to that of a very small battery. Under such constraints, traditional radio communication becomes extremely difficult. The signal would be so faint that even the most sensitive radio telescopes on Earth might struggle to distinguish it from background noise and interference. To address this, the design turns once again to efficiency. The light sail itself could serve as part of the communication system. By integrating optical or radio elements into its surface, the sail becomes a large antenna without adding significant mass. It could reflect carefully modulated light back toward Earth, forming a narrow optical signal across the distance. Another possibility involves using the sail as a phased array for radio transmission, shaping the outgoing signal into a focused beam. Even with these innovations, the amount of data that can be sent remains very limited. Transmitting a single detailed image could take days or even weeks, with data rates measured in only a few bits at a time. There would be no possibility of continuous video or large data streams. The probe would need to choose its observations carefully, sending only the most valuable information, perhaps a small number of images, measurements of atmospheric composition, or readings of magnetic and particle environments. Accuracy in pointing becomes essential. The probe must aim its signal precisely toward Earth across a distance of several light years. Even a slight error would cause the signal to miss entirely, disappearing into empty space. To do this, the spacecraft must know its orientation and predict where Earth will be when the signal arrives, accounting for both motion and the time it takes for light to travel. Small onboard sensors provide reference, while the computer calculates the required direction in advance. On Earth, receiving the signal would require dedicated observation. Large arrays of radio telescopes or powerful optical systems would need to focus on the expected arrival point, searching for extremely faint signals hidden within cosmic noise. Extracting useful data would demand careful processing and patience. Even at these high speeds, communication introduces a profound delay. Signals take years to travel between stars. This changes the nature of exploration entirely. In most missions within our solar system, communication happens with manageable delays. Instructions can be sent, data received, and adjustments made over time. But at interstellar distances, this connection becomes distant and slow. By the time a probe reaches its destination, decades will have passed since its launch. The people who designed the mission will have moved on, some no longer present to see its results. And any data sent back will take years more to arrive, completing a journey that unfolds not in moments, but across generations. By the time the probe arrives, everything on Earth will have changed. The original team will have moved through decades of their lives. Political priorities will have shifted many times. Technology will have advanced, and the systems used to design the mission may feel outdated by comparison. And yet, far away. The probe will continue executing instructions written long before, following a plan created by people who may no longer be involved in the field. During its brief encounter with Proxima Centauri, the spacecraft must operate entirely on its own. Every action is determined in advance: when to activate cameras, where to point them, how to collect data, and what to send back. If something unexpected appears, an unfamiliar feature, a strange atmospheric pattern, or something entirely unanticipated, the probe can only respond within the limits of its programming. There is no opportunity to ask for guidance, no way to pause and wait for instructions. By the time any signal reaches Earth and a response could be sent, the moment will already be gone. The probe will have passed through the system, continuing onward into the dark, its window of observation closed forever. When the first signals finally arrive, they will reach a world decades older than the one that sent the probe. The data will be received by scientists who may have been students, or even children. When the mission began, the context will have changed, priorities may have shifted, and new discoveries may have reshaped the questions we ask about the universe. And yet, those signals will still matter. They will carry information gathered from another star, answering questions that were asked many years earlier. This creates a unique challenge, not just technical, but human. How do we preserve knowledge across such spans of time? How do we ensure that future generations can understand and interpret data sent by systems designed long before their careers began? In this sense, the mission becomes multi-generational, not because people travel across the stars, but because the timeline itself stretches across generations. And at the end of that journey lies a world we still only partially understand. Proxima b orbits very close to its star, at a distance of about 4.5 million miles. But because that star is smaller and cooler than our Sun, the planet receives less energy than Earth does, placing it within a region where liquid water might exist. Its mass suggests a solid, rocky surface, a world that could, in some ways, resemble Earth, with landscapes shaped by familiar processes, but the similarities likely end there. The planet completes an orbit in just over 11 days, meaning its year passes in less than 2 weeks by our standards. This rapid motion, combined with its close orbit, creates an environment very different from the stable cycles we experience on Earth. And the star itself adds further uncertainty. Red dwarf stars are known for intense activity, producing powerful flares that release bursts of radiation. These events can dramatically alter the conditions on nearby planets, raising questions about whether such a world could truly support life. Proxima Centauri is known for frequent stellar flares, some so intense that they would expose a nearby planet to radiation levels far beyond anything Earth experiences. These bursts of energy could gradually strip away an atmosphere, alter surface chemistry, and create conditions that are far less hospitable to life as we understand it. Attempts to determine whether Proxima b still holds an atmosphere have produced uncertain results. Some observations suggest that it may have retained at least part of its gaseous envelope, despite constant exposure to stellar activity. Others indicate the opposite, that it could be a bare, rocky world, its atmosphere long since lost to space. The difficulty lies in how little we can directly observe. Even with our most advanced instruments, the planet remains a distant point of light. Its properties must be inferred indirectly, through small changes in the motion and brightness of its star. The presence of a magnetic field is another unanswered question. On Earth, our magnetic field protects the atmosphere from solar wind and shields life from harmful radiation. Whether Proxima b has a similar protective field remains unknown. Planets orbiting so close to red dwarf stars experience strong magnetic interactions, which could either strengthen or disrupt their own magnetic fields. The outcome would have major consequences for whether the planet can hold on to its atmosphere and maintain stable surface conditions. What these tiny probes might observe during a brief flyby could reshape how we understand habitability around red dwarf stars. Even if the planet turns out to be barren, with no atmosphere and no water, the data would still be valuable. It would help us understand how planets respond to the intense environments created by the most common type of star in our galaxy. There is also the question of how the planet rotates. Because it orbits so close to its star, it is likely tidally locked, meaning one side always faces the star while the other remains in permanent darkness. This happens when gravitational forces synchronize rotation and orbit, a process that occurs relatively quickly on astronomical timescales. Given the age of the system, Proxima b has likely spent billions of years in this state. The result would be a world divided into extremes. The side facing the star would receive constant energy, potentially reaching temperatures high enough to remove water and alter surface materials. The opposite side would remain in darkness, cooling to very low temperatures, limited only by how much heat the atmosphere, if present, could transport from one side to the other. Without an atmosphere, the contrast could be even more severe, with one hemisphere intensely hot and the other deeply frozen. Between these two extremes lies a narrow region, the boundary where day meets night. Here, the star would sit permanently on the horizon, neither rising nor setting. This twilight zone could offer more moderate conditions, depending on how heat is distributed across the planet. Some models suggest that if liquid water exists anywhere on such a world, it might be found in this region. If life were present, it could be concentrated in this narrow band, adapted to a constant, dim light and a sky where the star never moves. Atmospheric behavior on a tidally locked world would differ profoundly from anything we experience on Earth. The stark contrast between the permanently illuminated side and the endless night would drive powerful global winds. Heated air would rise on the day side, flow toward the dark hemisphere, cool and sink. then return along the surface in a continuous cycle. In theory, this circulation could redistribute enough heat to soften the extremes, preventing the bright side from becoming unbearably hot and the dark side from freezing completely. But how effective this process might be depends on details we do not yet know. The thickness and composition of the atmosphere would play a crucial role, and for now, these remain uncertain. The result could vary widely. The day side might be dominated by vast, dry expanses of exposed rock, with any surface water long evaporated and carried elsewhere. On the opposite side, water could accumulate as thick layers of ice, possibly stretching for miles, having slowly frozen out of the atmosphere over immense spans of time. Or, if the atmosphere is dense enough, it might smooth out these extremes, allowing liquid water to persist across broader regions despite the planet's locked rotation. Rotation itself introduces another question. On Earth, our magnetic field is generated in part by the motion of material within a rotating core. A tidally locked planet rotates far more slowly in this sense, which could weaken or even eliminate this process. Without a strong magnetic field, the planet would be far more exposed to stellar wind, allowing its atmosphere to erode gradually over time. And the star it orbits adds further intensity. Red dwarf stars are known for their unpredictability, releasing powerful flares that flood nearby space with radiation. These events occur when magnetic energy within the star is suddenly released, sending bursts of high-energy light and particles outward at immense speed. Observations show that Proxima Centauri produces such flares frequently, sometimes multiple times within a single day. The largest of these can briefly increase the star's brightness by several times. Because Proxima b orbits so close, it remains directly in the path of these outbursts. During a major flare, the planet could receive radiation levels thousands of times stronger than those experienced on Earth during even the most intense solar events. These bursts include not only visible light, but also high-energy radiation capable of breaking molecular bonds in both the atmosphere and surface materials. Charged particles follow soon after, striking the planet with significant force. Over long periods, repeated exposure to such events could gradually strip away the atmosphere, allowing gases to escape into space. While planets like Mars and Venus have lost portions of their atmospheres over time, the conditions around Proxima b are far more extreme, potentially accelerating this process dramatically. Any form of life in such an environment would face severe challenges. On Earth, life is protected by both a magnetic field and a relatively thick atmosphere. Without these layers of protection, organisms would need to tolerate intense radiation or find shelter beneath the surface or within water. There are microbes on Earth capable of surviving high levels of radiation, but even these may struggle under the constant exposure present on a world like this. And for any spacecraft sent to observe the planet, these same conditions present a risk. A probe arriving during a powerful flare could experience damage to its electronics, potentially ending its mission before it has the chance to gather meaningful data. These flares introduce another layer of uncertainty for any probe attempting to observe the system. Sensitive instruments could be affected in multiple ways. Cameras might be overwhelmed by sudden bursts of light. Solar cells could degrade under repeated particle impacts. Memory systems might experience errors as high-energy radiation disrupts stored data. And the difficulty is that these events cannot be predicted with precision. While we understand the general patterns of stellar activity, individual flares occur without warning. Some probes might arrive during relatively calm periods and gather clear observations, while others could encounter intense storms that limit what they are able to record. This behavior highlights how different red dwarf stars are from our own sun, and why simple definitions of habitability can be misleading. Being within a temperature range suitable for liquid water is only part of the picture. The nature of the star itself plays an equally important role in determining whether a planet can truly support life. Whether Proxima b still holds an atmosphere remains one of the most important unanswered questions. The combination of tidal locking, strong radiation, and the star's active early history may have stripped away much of its original gases. Without an atmosphere, the planet would be exposed directly to space, with no protection from radiation and no mechanism to balance temperature. In such a case, the difference between day and night would be extreme. Heat would build continuously on the side facing the star, while the opposite side would remain deeply frozen. Any water that once existed might now be locked as ice in permanent darkness, or lost entirely as vapor escaping into space. Detecting an atmosphere at such a distance is extremely difficult with current instruments. One method involves analyzing starlight as it passes through a planet's atmosphere, but this requires a very precise alignment that may not occur from our point of view, even when possible. The signals are faint and difficult to interpret. Other approaches attempt to study reflected light or heat emitted from the planet's surface, but these too push the limits of our technology. Some observations have hinted at the presence of an atmosphere, but the results remain uncertain and open to debate. Part of the challenge lies in the early life of the star itself. Young red dwarfs are highly active, producing frequent and intense flares for extended periods. Any planet forming in such an environment would face conditions that make it difficult to retain an atmosphere during its earliest stages. Whether Proxima b managed to hold onto its gases depends on several factors. Its mass may help, as stronger gravity can retain atmospheric particles more effectively. A magnetic field, if present, could offer protection by deflecting charged particles. The composition of the atmosphere also matters. Lighter gases escape more easily, while heavier molecules are more likely to remain. Models exploring these possibilities lead to very different outcomes. Some suggest the planet may still possess a thick atmosphere, while others indicate it could have lost most of it long ago. Other models suggest a different outcome, that planets orbiting red dwarf stars at such close distances may inevitably lose their atmospheres over long periods, regardless of how they began. The truth likely depends on details we cannot yet observe directly: the planet's exact mass, its internal structure, how it has evolved over time, the presence and strength of any magnetic field, and the history of its star's activity all play a role. To resolve this uncertainty, direct observation becomes essential. Probes passing through the system could look for signs of an atmosphere in several ways. They might detect how light bends or scatters near the edge of the planet, revealing whether gases surround it. Even the absence of such effects would be meaningful, showing a sharp, airless boundary and offering insight into how atmospheres survive, or fail to survive, around the most common stars in our galaxy. And even if Proxima b turns out to be entirely lifeless, the knowledge gained from studying it would still be profound. The search for life often captures attention, but it is only one part of a much broader scientific picture. Understanding how planets form, change, and interact with their stars remains a central question in planetary science. Each new world we examine adds another piece to that puzzle. Proxima b, in particular, offers a rare opportunity to study a planet orbiting a red dwarf, the most abundant type of star in the Milky Way. Since the majority of stars fall into this category, what we learn here applies to a vast number of systems across the galaxy. If planets around red dwarfs commonly lose their atmospheres or become inhospitable due to stellar activity, then the number of worlds capable of supporting life may be far smaller than we imagine. But if Proxima b has managed to retain a stable environment, even under harsh conditions, it suggests that many similar planets could also remain viable. Beyond questions of life, the planet's geological history could reveal much about how such worlds function. Tidal locking may influence internal processes. affecting heat flow and geological activity. The contrast between permanent day and night could shape unusual patterns of tectonics or volcanism. Water, if present, might behave in unfamiliar ways. It could gather as ice on the dark side, remain liquid in certain regions, or gradually escape into space. Each possibility offers insight into how planetary systems evolve under conditions very different from our own. If an atmosphere exists, its behavior would be equally revealing. Extreme differences in temperature between the two hemispheres could drive complex circulation patterns. Chemical reactions on the constantly illuminated side might produce compounds that do not form under more balanced conditions. Studying these processes would help us interpret the growing number of exoplanets discovered by missions such as Kepler and TESS. Observations from distant telescopes provide hints, but a close encounter, even a brief one, could transform those hints into understanding. The question of a magnetic field extends far beyond this single world. If Proxima b is able to generate one, despite its slow rotation and unfamiliar internal conditions, it would challenge what we think we understand about how planetary dynamos work. If it does not, then observing how stellar wind interacts directly with its atmosphere would offer rare insight into the process of atmospheric loss, something that has shaped worlds like Mars and Venus, and likely many others across the galaxy. Even the journey itself would carry scientific value. A functioning probe traveling through interstellar space for decades would measure the environment between stars directly, its density, its composition, the structure of its magnetic fields, and the behavior of particles drifting through that vast space. These measurements would refine our understanding of the medium that fills the galaxy and the conditions any future mission must pass through. The technological achievements alone would be transformative, demonstrating that such small spacecraft can survive for decades, that laser-driven propulsion can reach extreme speeds, and that communication across light years is possible, would reshape how we think about exploring deep space. Studying a planet in another star system also provides something we cannot obtain by looking only at our own. Our solar system offers a single example, one set of outcomes shaped by one star and one set of initial conditions. We have learned a great deal from it, but we cannot know which features are universal and which are unique without comparison. Proxima b offers that opportunity. Most distant planets we detect today appear only as faint signals, their properties inferred from indirect measurements. We estimate their size, their mass, and their orbit, but we do not see them in detail. A close flyby would change that. It could provide images of the surface or cloud layers, measurements of atmospheric composition, readings of magnetic fields, and maps of temperature across the planet. Instead of relying on inference, we would begin to observe directly. This kind of data would deepen our understanding of how rocky planets form and evolve. Did Proxima b form where it now orbits? Or did it migrate inward over time? Has it experienced impacts similar to those that shaped Earth in its early history? What role has water played, if any, in its development? Comparing Proxima b to Earth becomes especially meaningful because of their similarities and differences. Both may be rocky worlds with comparable mass, but they exist in very different environments. Earth orbits a stable star at a comfortable distance, receiving relatively steady energy. Proxima b, by contrast, orbits much closer to a smaller, more active star, exposed to frequent flares and stronger magnetic interactions. Any differences we observe between the two worlds could reveal how much a star's nature influences the outcome of planetary evolution. The comparison goes even further, reaching into the very idea of what makes a world habitable. We still do not know which features of Earth are essential for life, and which are simply coincidences. Does life require a large moon to stabilize a planet's tilt, or plate tectonics to regulate climate over long periods? Each difference we observe helps refine our understanding of what truly matters. Beyond a single planet, Proxima b may become part of a growing group of nearby worlds that we can study in detail. Over time, this could build a clearer picture of how planets behave across our region of the galaxy, turning isolated discoveries into a broader understanding. The astronomer Carl Sagan once suggested that by the time humanity is ready to reach other stars, we will have changed in fundamental ways, not just in technology, but in how we think and act as a species. Interstellar exploration demands more than advanced machines. It requires the ability to think far beyond individual lifetimes, to commit to projects whose outcomes may only be seen by future generations. Even a relatively modest effort like Breakthrough Starshot would require decades of preparation. Designing and building the necessary systems, maintaining cooperation across nations, and sustaining funding through changing political and economic conditions. These are challenges that extend far beyond engineering. Those who begin such work may never see its completion. This requires a shift away from short-term thinking, toward a mindset that values long-term goals and shared progress. It is not only a technical challenge, but a cultural one. A civilization capable of undertaking such missions would likely have learned to manage many of the risks that currently threaten its stability. Issues like environmental change, conflict, and resource limitations do not directly prevent interstellar travel, but they affect whether a society can remain stable long enough to pursue it. Planning across decades becomes difficult if the future itself feels uncertain. Stability, cooperation, and foresight become as important as technology. There is also a broader shift in perspective. To reach the stars, we must begin to see ourselves less as separate groups and more as a single species sharing one world. This does not erase differences, but it does require recognizing a shared interest in survival and progress. We have already seen glimpses of this cooperation in projects like the International Space Station, where former rivals work together toward a common goal. Interstellar exploration would require that level of cooperation to grow even further. And perhaps most importantly, it requires patience. Our technological civilization is still very young. In cosmic terms, we have only just begun to step beyond our planet, accepting that reaching the stars may take not just years, but generations, is part of understanding our place in the universe. A truly mature civilization learns to balance hope for what may come with an honest understanding of what is possible now. Perhaps the deeper question is not only whether we can reach other stars, but whether a short-lived species can commit to goals that extend far beyond any single lifetime. Can we begin something knowing we will never see its end? Can we create, build, and explore for the sake of those who come long after us? The effort to reach Proxima b, whether it succeeds or fails, brings these questions into focus. And in doing so, it may shape us into something more patient, more thoughtful, and more capable of seeing beyond ourselves. Because the reality remains difficult. With everything we understand today, the journey to such a distant world may never become truly practical. The barriers are not simply technical problems waiting to be solved. They are rooted in the structure of the universe itself. And yet, throughout history, humanity has faced challenges that once seemed impossible, not because success was guaranteed, but because the attempt itself carried meaning. Builders of great structures began their work knowing it would outlast them. Explorers set out without certainty, driven by curiosity rather than assurance. Each generation inherits the limits of the one before, and then slowly extends them. What seems unreachable today can become the foundation for tomorrow. The obstacles before us now are real. The immense energy required, the vast distances, the delays in communication, and the harsh environment between the stars are not illusions. They define the scale of what we are attempting. It is possible that we may never develop a way to travel easily between stars. The universe may be arranged in such a way that each system remains largely isolated, separated by distances too great to cross in any practical sense. There may be limits we cannot overcome, no matter how much we learn. But even so, the effort carries value. The technologies developed along the way, new materials, more efficient systems, better methods of navigation and communication, would shape life here at home. The cooperation required to pursue such goals could strengthen our ability to face challenges on our own planet. More than that, the attempt reflects something fundamental about us. It is the same impulse that once carried humans across continents and oceans and eventually beyond Earth itself. A quiet refusal to remain still. To abandon the idea of reaching other stars simply because it is difficult would be to accept a boundary without ever testing it, to decide, in advance, how far our story can go. And perhaps this connects to a deeper mystery. When we look into the universe, we do not see clear signs of other civilizations. This silence raises questions. It may be that many reach a certain point, then turn inward, deciding that the journey is too long, too uncertain, or too costly. Or perhaps some continue, pushing forward despite the difficulty, becoming something different in the process. We cannot know which path leads further unless we take it ourselves. Proxima b, distant and uncertain, is more than a destination. It is a measure of what we are willing to attempt. A question asked not just of our technology, but of our patience, our cooperation, and our imagination. Whether we ever reach it or not, the act of trying may be what matters most, because in reaching towards something so far away, we begin to understand what it means to think beyond a single lifetime, to invest in a future we may never see, and to look at the stars not as limits, but as possibilities. And so we gently arrive at the end of this quiet journey, drifting through the immense darkness that stretches between us and Proxima b. We have wandered through the scale of distance, the limits of physics, the fragile designs of tiny spacecraft, and the strange nature of a distant world locked between endless day and endless night. A world shaped by radiation and uncertainty, yet still holding the quiet possibility of discovery. The distance remains almost beyond comprehension. More than 4 light-years of empty space. A vast separation that even our fastest machines would take thousands upon thousands of years to cross. Even our most hopeful ideas require decades of effort, cooperation across nations, and technologies only just beginning to take form. And yet, within that difficulty, there is something deeply human. We are the kind of beings who look toward distant lights and imagine standing beneath them. The same curiosity that once carried people across unknown oceans now reaches outward into the stars. As you begin to settle into rest, let that thought drift softly through your mind. You exist in a brief and remarkable moment, aware enough to imagine journeys across the galaxy. The very atoms that make you were once part of ancient stars, scattered across space long before Earth was formed. In a sense, you have already traveled farther than any spacecraft we have ever built. Whether we one day reach Proxima b or whether it remains forever distant does not take away from the wonder of the question itself. The universe has given us the ability to imagine, to ask, and to reach beyond what we can touch. So rest now. With that quiet awareness, you are part of something vast, something still unfolding, a universe that, for a moment, has become aware of itself through you. Sleep peacefully, traveler. The stars will still be waiting when you wake.